Hello, this is Alan Boris, and this is a section on the prehistory part on radiocarbon dating that I've produced for you to be sure you have a clear understanding of how radiocarbon dating works. This is a graph done by Douglas Rieger and myself in a publication in 1996 that is in your reading packet. That shows at the time all of the radiocarbon dates for Cook Inlet associated with archaeological sites. And what I'd like to do is go over the basics of radiocarbon dating so you're clear how it works, because you should be asking the question when I say something is 1,000 years old or 2,000 years old or whatever, how do you know? And so this is more on the lines of the how do you know part of that question. I think it's true that almost all of the dates for Cook Inlet archaeology are from carbon-14 dating. So that's what we'll focus on, is carbon-14 dating. This is a schematic. I lifted it off the internet that shows the process of carbon-14 production. So it starts in the upper left. Carbon-14 is produced in the atmosphere. Energy packets from the sun, muons, nuons, they have a lot of different names that are produced from solar energy, strike the atmosphere, and some of them strike nitrogen, which has an atomic number of 14, meaning it has 7 protons and 7 neutrons. One of those protons is changed to a neutron, and the consequence of that is it's no longer nitrogen, but now it's carbon. Normal carbon is carbon-12, 6 protons, 6 neutrons. But this derives from nitrogen, so it's an isotope, a radioactive isotope, carbon-14, 6 protons and 8 neutrons. So its production is in the upper atmosphere. It's a very small percentage. It's less than 0.1%. I forget the exact percentage, but nevertheless it's measurable. There's a big atmosphere up there. And that carbon then, to step 2, oxidizes and forms carbon dioxide. So a part of the carbon dioxide that's in our atmosphere is radioactive carbon, carbon-14. So going on to the next step, that radioactive carbon-14 is used by plants in photosynthesis. Photosynthesis involves taking in carbon dioxide, keeping the carbon, and giving off the oxygen. Process of photosynthesis, but also and that incorporates some of that carbon into the plant tissues. So every living plant today has some radioactive carbon in it. In addition, there is a lot of the carbon-14, most of the carbon-14 is absorbed by the oceans. So that follows a little different process. It's absorbed directly into seawater and accumulates in ocean basins. So marine carbon dating is a little different than terrestrial radiocarbon dating. So to go back to the land, the animals consume the plants, some of which are radioactive, have a little bit of this low-level radiation that's derived from carbon-14, and that's incorporated into the animal bone and other tissues through various metabolic processes. So all herbivores have some radioactive carbon in them, and then carnivores eat the herbivores, so they have radioactive carbon in them. And that process continues as long as the organism is alive. It will continue to take in fresh, as it were, radioactive carbon. Very small percentage, but nevertheless measurable. So when an animal dies, their metabolism ceases, of course, and the tissues stop incorporating carbon-14, And that carbon-14 then decays back to nitrogen-14, and the proportion of carbon begins to decrease. The proportion of radioactive carbon begins to decrease. That results in radioactive decay. As all radioactive decay, carbon-14 in this case spontaneously reverts from the parent isotope to the daughter isotope. The parent isotope is carbon-14, the daughter isotope is nitrogen-14. What happens is described in this chart here. Here's carbon-14, 6 protons, 8 neutrons, and that will change back to nitrogen-14, 7 protons and 7 neutrons, and give off an antineutrino and an electron. So that's what's measurable in this process. That's the decay process. And we know that a modern sample, shall we say, a modern person, a modern dog, a modern tree, will tick away at about 12 ticks a minute. And that's these energy packets. If I were to hold a Geiger counter up to you within about a foot and a half of you, I could measure you ticking away at 12 ticks a minute. Same with me. If I held that same Geiger counter up to me or my dog Sammy, 12 ticks a minute. That begins to wind down after the organism dies, and so after when it's 50% is changed, it's going to tick, of course, at 6 ticks a minute. We know that process takes 5,730 years. That's called a half-life. So from the time an organism dies to when half of it has changed from carbon-14 to nitrogen-14, 5,730 years have passed. That's measured by looking at very ancient trees who live very long time spans, and they literally date the tree rings. So another 5,730 years, half of the half. So now it's ticking at about 3 ticks a minute, and a tick and a half a minute, and so on until it's not ticking at all. There is a way to enhance this so you can push the date back to between 50 to 80,000 years old, but beyond that there is no more radioactive decay, so other types of decay will be necessary. So here's the process of collecting the sample. These are 4 hearths. This is a plan view. This is from 4 sites near the mouth of the Kenai River. This is right in the heart of Kenai. And then there's a ridge that goes along here. And there are a number of Denina sites that exist along this ridge that I excavated with a group of students from the college in 1991. So this hearth is from a Denina house at this site here. And this is the top view. This is what it looked like as we excavated. This is the remains of essentially a log crib filled with sand. That's how the Denina built their hearths inside the house. I'll show you pictures of that later when we talk about Denina archaeology. And as the house is abandoned and decays, the whole log crib decomposes, and so you see this sort of lens. So this is a cross section here. This is a plan view. This lens of sand and charcoal and sometimes fire-cracked rock. And often, almost always, the last fire is right at the top in terms of this pithy charcoal. So when we open up the sod inside one of these houses, we're very careful because almost right under the sod surface, that's where the charcoal will be. I believe this particular picture is actually this drawing right here at another site. I think it's this site right here. But it's been a number of years and I tend to forget. So going back to this one then, that arrow points to where we took the carbon for that particular date. This designation WSU 4142 is an indicator of the lab that we sent it to, and that's the lab number. So at another house, here's another sample that we took, and that's where we got it from. It's important to record for other archaeologists to know where you got the sample. And this one, and this one. So these are all pithy charcoal. They're all spruce. I've split enough firewood so I can tell what spruce looks like, and if I couldn't, I'd bring in an expert and who could tell from the cellular structure what species it is, but we know this to be all spruce, and that's not surprising. So they're burning spruce in the hearth, not unlike you and I burn spruce in our fireplaces today. It's important to note that it's spruce because what we're dating is when, in this case, the tree died. What we're interested in is when the people lived there. And that's not the same. The tree could have been cut down 10 years before, or 20 years before, and then burned in the hearth. But that margin of error is fine for our purposes. In some cases, archaeologists have submitted material from Denina hearths, and it turned out, and it dated very old, much older than anything we know about, and it turned out that what they were dating was beech coal. So the beech coal ash was mixing with the charcoal and pushing the date back, because the beech coal formed 90,000 years ago. The date was right, but the association was wrong. So in this case, one has to be very careful to associate what you're dating with the culture that you're interested in. You can sometimes date artifacts, you can date other things, and that's good, although you do have to sacrifice the material for the dating, and so that can be a problem. Charcoal is pretty good. It's pretty abundant. It's pretty easy to collect. It's pretty easy to clean. So we collect it, we take it back to the lab here, or a lab, wherever you're working out of. Let it dry, because we don't want mold to form, which would cause contaminate the carbon, radioactive carbon percentages. And I or a student or someone, volunteer, will pick out, and once it's dry, we'll pick out the bits of obvious rootlets or other recent organic material, because we just want the material from what the Denina burned, in this case Denina. Wrap it up and label it, and I forget what it costs now. I think it's about $300 for a sample, and you send it off to a lab and they will process it. And what you will get back, we'll go to the next slide, is something like this. You will get a radiocarbon age back. So this is that first house. It was pithy charcoal from the central fire hearth. That's where it was located. And the radiocarbon age is 350 plus or minus 90 years. And this one was 240 plus or minus 130, 380 plus or minus 90, 540 plus or minus 90, all from pithy charcoal from the houses. We then have to calibrate those ages if we want a date in terms of AD or BC. So let's talk about calibration. It turns out that radiocarbon years are not identical to calendar years, so they have to be calibrated. This is a scale in AD BC terms, back to 6000 BC. If this line here would correspond to the same date, 1000 years, 1000 BC, this is 1000 BC. So what's plotted here is what the radiocarbon dates worldwide, what the radiocarbon dates come in at. So anything that is around 800 AD is going to be too young by about 100 years or so. Anything older than that is going to date too old. And we know that, again, from dating. It's mostly bristlecone pine from the areas of Nevada and that part of the world, the Great Basin, that are very old trees and very well preserved. So there's this disconnect, but we can account for that by calibration. Essentially, you put in the date that you've got, the radiocarbon date, and the computer spits out the calendar date. This follows, by the way, for you math fans, a sine wave, and it's thought that if it were any older it would probably come back up again, and so it's some kind of consistent variation in something. So what would cause this change? I'm not sure what the recent research is, but because the production of carbon-14 is in the upper atmosphere, and by solar radiation, it's likely caused by solar radiation variances over time. More or less solar radiation for some kind of reason fluctuating from the sun. A natural process, which probably also, by the way, affects natural climate change. But for our purposes, it's known. We can calibrate dates, we can then account for them. So that's why the calibration date, and it's more understandable to give an AD BC type date than it is to give the plus or minus date. So in effect, the sample is, as I say, it's bound up and cleaned and wrapped up. I use aluminum foil as the first barrier of defense. You don't want it to get wet. Put it in some kind of plastic jar of some kind, and you label it very clearly. Send it off to a radiocarbon dating lab like this, and essentially what they'll do there is they will distill it. They will burn it in the absence of oxygen and gasify it. And they'll put it in a chamber. I'm not sure which chamber is which here. I've never actually been to a carbon dating lab. But they put it in a chamber where they have that Geiger counter. Remember, if it's a recent sample, it's going to tick at 12 ticks a minute. And so on down the line. So they count the ticks per minute. And I believe they leave it in for 3 days. And then they calculate a average ticks per minute and a standard deviation of those ticks per minute, and that's the information you get. That standard deviation is the plus or minus from the average ticks per minute. So to go back to this chart, this is the same one I showed at the beginning. The horizontal line is the date, the average date after that whole process went on, and the vertical line is the standard deviation. This sample had a very large standard deviation. Some of these had a very low standard deviation. If I could go back to the previous slide, I want to also mention There is a more expensive, more accurate way of dating, which involves a mass spectrometer. You don't need very much carbon to do that. For the process I described here, you need, it's a half a cup is good. They usually take less than that, but a quarter of a cup or a half a cup, something like that. But you can just take a very small amount of carbon if it's from an artifact or something very precious. You don't want to destroy it, or you want to be very accurate. And it costs, as I say, costs more, and they'll essentially shoot atoms through a mass spectrometer and measure the percentage of carbon-14 atoms to nitrogen-14 atoms, and from there make that same calculation based on the half-life of carbon-14. The Shroud of Turin, for example, was dated that way because the owners didn't want it sacrificed, so they took one thread and dated it, and I believe it didn't come out to be as old as people thought it was. So that's the way evidence is. So I'm going to skip back to where we were. So we can plot these, and we associate it with the culture. So these are the Riverine Kachemak dates, and they range from 1000 BC to 1000 AD. So we can say with great degree of confidence the Riverine Kachemak people were around for that time period. As we do new excavations and gather more information, we submit them. They should fall into this time range. Maybe we're wrong, maybe it's a little older. That puts that line down further. So far, that hasn't happened for some of these. We can say with a high degree of confidence that the sedentary Denina appear at 1000 AD, and this is for Cook Inlet. Now that doesn't mean this is when the Denina first appear. They likely, before that time, were nomadic caribou hunters. But for whatever reason, one of these unanswered questions, they figured out how to catch salmon and freeze salmon for preservation about 1000 AD. So they start living in log houses and having fire hearths like the ones I showed you, and from this we get dates that date the sedentary Denina. This is Lower Cook Inlet, this is Kachemak Bay. We have a few Denina sites there, and they date in the same time range. This is the Marine Kachemak tradition that you will also have a PowerPoint lecture on. There's fewer dates from the Marine Kachemak tradition. This is one, I'll show you in that lecture, this recent date here. Bill and Karen Workman think that possibly this may have been depopulated, and maybe that's an erroneous date. It could be. I think it's a good date, but more work will tell. People will excavate other Marine Kachemak sites and either fill in this gap here or find out, no, that might be an erroneous date. Need more dates from the earlier time period. This is not a lot of dates. These are not a lot of dates to go by. This is a culture, a pottery-bearing culture, that's sort of anomalous. So far it's just given this name. Need more information on that, as well as these lesser known sites around from the earlier time period. So there's a lot of information to be gathered from further archaeology in Cook Inlet, and part of it has to do with fleshing out these earlier time periods and what they represent. Now remember, these are the dates from 1996. There are more dates now. There's more information, so that's why we keep doing archaeology. So I hope that gives you a good primer on how radiocarbon dating works and how it's been applied to Cook Inlet.